Hi everyone, this is going to be a video walkthrough for exam prep discussion 9 on heaps and tries. Okay, I'll be covering questions 1 and 2 in this recording. Let's dive in. So the first question states, remove min has a best case runtime of blank and a worst case runtime of blank. Okay, so let's first recall how remove min works. Suppose we have some heap. I'm just going to fill in all of the elements with circles. Okay, so if we call remove min, what happens is we remove the minimum, then we promote the rightmost, bottommost element to the top temporarily, and then we'll bubble him or her down until they're in their happy spot. Okay, so looking at numbers, how that would look is, let's say we have 1, 2, let's say 99, 100, 3, 4, 5. Okay, what'll happen is we'll remove 1, we'll move 5 to the top, and then we will move 5 down right here, right? We'll move 5 there, and then 2 would go to the top, right? So that's like the process of remove min. We could think about remove min's worst case runtime as us doing as many swaps as possible. The maximum number of swaps we can do is until this element 5 goes to the very bottom of the heap, right? The total number of swaps for 5 to go to the very bottom of the heap is log n swaps if there's n elements in the heap, because log n is the height of the tree. Okay, so for the worst case runtime, we see it's log n, because the element that goes to the top could go all the way down to the bottom and do log n operations. So the best case runtime is a bit trickier, but we can think about, let's suppose we have a heap where all of the elements are duplicates, okay? Then when we remove the 2 from the top, what we'll do is we'll promote the 2 from the bottom to the top, and it'll just stay there. So we can see here that the best case runtime is constant time. Perfect. So does anyone have any questions about that? Any questions?
I have a question.
Okay, one question. Go for it.
If there are distinct elements in the min heap, is the best case runtime of remove min still constant time?
Okay, good question. So the question was, to reiterate, if they are distinct elements in the min heap, is the best case runtime still constant time? Okay, let's look at that situation. Okay, so suppose there's distinct elements in the min heap. Let's say that we have 1, 2, 3, then we have a ton of elements on this subtree and a ton of elements here. I'm going to argue it's still constant time best case, because we're going to be doing we can be doing 2 swaps in a potential situation, okay? So let's quickly dive into the situation so we can see. Suppose we have this min heap and we have 2 over here, and then we have some really big elements that are children of 2. Let's say 100 and 101, okay? And then let's say that the rightmost bottommost element is the number 99, okay? What'll happen here is we'll call remove min, 1 will leave. Then what we'll do is promote 99 to the top, right? Then 99 will swap with 2, and then what will happen is 99 will stay right here at the second level, okay? So looking at this example, you can see that if the element that we promote in the bottom right corner is less than these 2 elements in the other subtree at the third level, this element 99 will stay where it is, and it'll only do 2 swaps, right? It'll first go to the top, and then it'll swap with 2. So you guys can kind of see here that it's not always the case that we go down to the bottom of the heap upon a remove min operation. There is a chance, even if the heap has distinct elements, that the number we promote to the top only needs to do 1 swap until it's back in a happy place. Okay, perfect. So let's keep going for the sake of time. Insert has a best case runtime of blank and a worst case runtime of blank. Perfect. Let's first quickly recall how insert works. If we have any heap, insert basically says, let's go to the next open spot in the heap, and then we'll put the number there, okay? So let's say we want to insert the number 1000. We'll say 1000, go to the next open spot. And we see here, if the number we insert is really, really big, what will happen is we don't have to do any work, right? It's happy where it is. So the best case runtime occurs when we insert an element that's big, and we could just keep it as is, and there's no swimming that needs to be done, okay? So the best case runtime is constant in the situation we insert a really big number. The worst case runtime is the situation in which the number we insert, let's say 0 for the sake of example, has to iterate all the way to the top of the tree, right? In order for 0 to go all the way to the top of the tree, it has to do log n swaps, because log n is the height of a heap with n elements. Okay, I also want to touch upon the fact that I'm using a theta notation because that was a question I received in a couple discussions. So the reason I'm using a theta notation here is when we talk about the best case and worst case runtime of a function, if the best case runtime always takes the same amount of time, we can give it a theta bound, right? Because that's how a theta bound works. The best case runtime of a function will always be constant time, right? Because the situation in me inserting a really big element in the case of insert is always constant time. So we can give a theta bound. Okay, let's keep going. So there's two types of traversals that will output the elements in sorted order. And without loss of generality, let's assume that there are no duplicates and the height is, I don't know, at least 3 of the heap. Okay, so looking at this, now it's a bit more specific, but I think the problem is a bit better because of it. Let's first recall the 4 types of traversals that we've covered in class. We have a pre, a post, an in-order traversal, and a level order. Okay? So if we have any heap, let's say we have some arbitrary heap, right? How a pre-order traversal work, it'll output this element, right? This is the order that a pre-order traversal would output the elements, okay? Like an in-order traversal would output the elements in that ordering, right? Just a quick refresher. A post order would output the elements. A post order is a bit trickier, but it'll output the elements in, I missed it. Yeah, that's the order for a post order. And then quickly a refresher on level order. A level order will go level by level. Okay, so quick refresher on traversals. What I want to emphasize for this problem is that if the elements are outputted in sorted order, the first thing that needs to be outputted in the heap is this topmost element right here. The reason for that is the topmost element in any heap that doesn't have duplicates must be the smallest element in that data structure, right? It's the smallest element that exists. So to output things in sorted order, this element must be outputted first. If we look at these traversals, we can eliminate a post order and an in-order traversal because of the fact that post order and in-order traversals first visit the left before like marking or visiting the current node. So with that in mind, there's only 2 possible traversals that are left, and we can put them in for our answers. So we can say a pre-order or level order traversal. But I still haven't showed you guys an example of when that would actually occur. So let's quickly create examples for both. So let's say we have some tree, like, let's say we have 1, 2, 3, 4, 5, 6, 7. Okay, perfect. So let's do a pre-order traversal on this tree. We'll get 1, 2, 3, 4, 5, 6, 7, which is in sorted order. Okay, let's look at one more tree for the level order. If we look at this tree, we see that 1, it's a heap, right? As with the tree on the left. And when we do a level order traversal, the elements are outputted in sorted order. Okay, perfect. Let's move on to the next part. The 4th smallest element in a min heap can appear in blank places in the heap. So the number 1000 is just arbitrarily large. let's look at an example of a really, really large min heap, and then we'll try to figure out a solution. Okay. So I'm just drawing a big min heap, and then we'll figure out some idea from here. Okay, so perfect. Here's some random min heap. I like to use circles to just represent, I don't know, arbitrary numbers. And let's play a little game. How the game will work is I'll highlight a spot in the min heap, and you guys think to yourselves, yes, the fourth smallest element can go there, or no, it cannot. Okay, let's start at the root. Can the fourth smallest element in the min heap possibly live here? So the answer is no. The root of a min heap that has distinct elements must be the smallest element in the min heap. As such, it can't be the fourth smallest. So what we can do is we can eliminate the top. Okay, let's keep playing. Let's say I put an element here. Can this be a valid spot for the fourth smallest element in the min heap? Yes, it can. The reason it can is, let's say the top was 1, 2, 3, and then 4. You guys see it's a valid situation, right? Okay, let's keep playing. Let's say I decide to put it here. Okay, is this valid? Yeah, it's valid, because we can do 1, 2, 3. Actually, let's do 1, 2, 3, 4, right? So it works perfectly fine. And another thing that I want to note is there's no difference between this element and this element, right? If they're both on the second level, if one of them is a valid spot, the other one also must be a valid spot, right? So with that, we figured out 6 places that we can put the fourth smallest element so far, right? The second level is all valid, and the third level is also all valid. So let's say, can a point be on the fourth level? Is that a valid spot? Okay, so if I put something on the fourth level, right? If I put something on this leftmost spot, if this spot is valid, it means every spot on the fourth level is valid, okay? So if something was here, the root could be 1, this could be 2, this could be 3, and this could be 4, and here would be the fourth smallest element, right? Okay, so with that in mind, we can safely conclude that all elements on the fourth level are also valid. And we can see that once we get to the fifth level, this is the first level that we can safely eliminate on the bottom half of the heap, right? So when we get to the fifth level, we know we can eliminate this spot and every spot on the fifth level. The reason for this is any spot, any number on the fifth level must be greater than all of its parents, right? So looking at a number here, let's say 5, in order for 5 to be here, it must have been greater than this element, this element, this element, and this element. In other words, it must be greater than all of the 4 elements above it, right? All of its parents. And we see that best case, it's the fifth smallest element. It can't be the fourth smallest. Okay, sorry about my Slack. I'm going to quickly quit out of it. Okay, so let's get back to this example. We can eliminate the fifth level because this number must be at least the fifth smallest, right? Okay, and with that in mind, we can also eliminate all of the levels below it, right? So what we can put here is the total number of elements, the total number of spots the fourth smallest element can go are the total number of places on the second, third, and fourth levels, which is 2 plus 4 plus 8, which is 14. Right? We got 14 because there's 2 spots, 4 spots here, and 8 spots. So we add those up. Nice. Okay, that question was pretty tricky. So let's look at the last one, which sadly is also tricky. Okay. Given a min heap with 2 to the n minus 1 distinct elements, for an element to be on the second level, it must be less than blank elements and greater than blank elements. Okay, so let's look at an arbitrary min heap. Okay. Okay, here is my attempt at drawing a arbitrary min heap, and I'm going to partition it into 2 subtrees. We'll call this subtree B, and we will call the subtree on the left subtree A. Okay? So now let's look at an element on the second level. Okay. Let's just choose this one on the right. Okay. So for this element to be on the second level, it must be greater than the root, right? That's the first, I think the easiest observation to make is that this element right here, actually let's use the proper color. We see that this element right here must be greater than the root because otherwise it would be the root, right? And we don't know anything else besides that on the elements it's greater than, right? It could be the second smallest thing in the min heap, so we can only say that it's greater than one element. So what elements is it less than? We know it must be less than its children, right? We can say it's less than these two elements, and continuing off this logic, we can say that it's less than everything in this subtree, right? So the next question that arises is how many elements are in this subtree, right? What is the total number of elements that are here? Okay, so in order to figure out the total number of elements that were here, we should first figure out that is this bottom level, like if it ends right here, you guys kind of see what I mean? Like if it ends right here, then there's gonna be some weird edge cases, okay? So it's like a lot to take into account, perfectly fine. We know there's 2 to the n minus 1 distinct elements in the heap, okay? There's probably a reason that the creator of this question chose such a specific number, right? So let's see why. If n is equal to 3, what we'll notice is there's 2 to the 3, 8, minus 1, 7 elements in the heap, and the heap will look like so. Okay? So the cool property here, there's two takeaways, is that for any value of n, we know that number of elements on the bottom level is completely full, right? In other words, like the bottom level of this heap will be completely full. So what we can say is that when we're looking at the bottom level here, it goes all the way to the very end. So we can say that A is equal to B in terms of size, right? Both A and B are of the same size because the heap is completely like full for each level. Okay. So with this in mind, let's try to figure out the size of B. And let's do some quick operations here. Okay, I'm going to quickly get rid of that. Okay. So let's clearing up some space because I'm going to have to do some math. Exciting. Okay. We know there's 2 to the n minus 1 elements in the heap. Okay? That's given to us. The next thing that we want to do is there's 2 to the n minus 1 elements in A and B, right? Oh, just kidding, 2 to the n minus 2. Okay, that's the second thing we can easily conclude by subtracting the root, subtracting 1 to remove the root. Okay, the next thing that I'm going to conclude is there's 2 to the n minus 2 divided by 2 elements in B, right? We can conclude this because B and A are the same size, so we can just divide by 2, okay? The next thing that we can conclude, actually, let's first do simplification. Just doing some math, we can say that there's 2 to the n minus 1 minus 1 elements in B. Okay, same thing, just simplification. The next thing we can conclude is the total number of elements that are less than this element on the second level is everything in B minus 1. So there's 2 to the n minus 1 elements that are in B and less than, let's just call this B sub 2. Perfect. And we have to subtract 2. Perfect. Because we're losing that one element. Okay. So with this in mind, we can say the answer is 2 to the n minus 1 minus 2. Okay. Phew. Okay, let's move on to the next part. For something to be on the bottom level, it must be less than blank elements, and it must be greater than blank elements. Actually, let me first clear some of this work. Okay, perfect. So let's look at an arbitrary element on the bottom level. Let's say that we choose this element right here. For it to be at the bottom level, it must be less than, should it be less than anything? It might be the biggest thing in the heap, right? In that case, it's less than 0 elements, right? Because it's the biggest thing. So who is it greater than? It must be greater than all of the elements that are directly above it, right? It must be greater than all of its parents. That's the only thing we can conclude. We have no idea about the relationship of this element and, I don't know, this one right here, right? We just don't know anything about it. Because the only property of a min heap is that a parent is less than or equal to its child, or in this case, since the tree only contains distinct elements, it's less than its child. So we know that an element at the bottom level must be greater than all of its parents. So how many parents are there? Well, looking at n equals 3, we see that for an element at the bottom level, it has 2 parents, right? And if you guys play around with more examples, you guys will see that an element at the bottom level will have n minus 1 parents. So it must be greater than n minus 1 elements. Phew, okay. That's all for question 1. Let's move on to question 2. Actually, let's do a new recording for that. That's probably better for y'all.